A huge part of this course that you'll notice throughout the semester is the idea of scheduling. And to motivate that and to discuss some of the core underlying fundamentals of that, we're going to discuss memory as it applies to the processor. So just to reiterate, we discussed that instructions themselves are just pieces of data, and it is purely in how they are interpreted that differentiate them from data. They are still blocks of bits stored in some memory location somewhere. We've talked about the instruction cycle, how that works, and we've also discussed some important registers, the program counter and the instruction register. When it comes to memory, there is a fundamental trade-off between size and speed. The reality is that when you get more and more memory that you can address, it takes longer and longer to access a piece of data at a particular address. On top of that, in realistic scenarios, we also have a cost factor we have to consider. Even if we are able to get a better size to speed ratio, it will turn out that that will come at an increased cost in dollar amounts or resources. So the reality is that if we're trying to build a reasonable cost machine and we want a large amount of data stored somewhere, we will have to deal with the fact that it is going to take longer for us to get data from that storage. Or if we want something to be accessed quickly, if that's a requirement, then we will have to deal with having less data accessible in that piece of memory. Those trade-offs are fundamental, and they are important to what we're going to discuss throughout this video, and they will motivate a lot of things that we discuss throughout this course. What I am now going to talk about is a set of rules of thumb that we utilize and take as assumptions, and thus, if they are true, we have ways of dealing with some of the problems associated with the trade-offs that I just talked about before. And the basic rule of thumb is the concept of locality. And there are two key aspects of locality. But basically, the idea is that the probability of us accessing, or the likelihood of us accessing a particular piece of memory is not uniform, and that we can utilize some of this unevenness in the likelihood of accessing particular addresses to deal with and come up with a special way of dealing with some of the trade-offs so that we can get something that in reality works a little bit faster for a little bit larger than we would have been able to deal with just having a single block of memory. So spatial locality is simply that if we have used, let's say we have a big block of memory here, if we have used the data just here, then it is likely that we will use the data adjacent to it. In fact, the idea is that it is more likely that we will use the data adjacent to the data we have just used than that we will use data much further away. So simply restated, if we've used the data at memory location X, then the data at memory location X plus 1 is more likely to be needed fairly soon than the data at location X plus 1000, for instance. And that's spatial locality, i.e. we are likely to use data that are close together. We're more likely to use data that is close together than we are to use data further and further apart. And if this is actually true in a particular application, then we can gain some advantages by having all of this data here in a fast bit of storage temporarily. The second kind of important locality is temporal locality. The idea here is that if we just used a piece of data, then it's likely that we might be using that data again soon. i.e., if I'm working through something where I'm summing up the values in a list, then I am keeping that temporary summation somewhere here. So my partial sum might be stored in a particular location. Whilst I'm moving through that, each time I'm adding back to that sum again. So I'm going to need to access that sum in order to add the new value to it, and then I'm going to need to store back into that same location again. So here we have a situation with high temporal locality. So, if it turns out that these two principles of locality, spatial and temporal locality, are true, then we can do something called caching, which will increase our ability to get a certain speed access from memory, whilst also having a higher amount of memory without just using a very large and expensive piece of fast memory. The idea here is caching. Now, many of you may already know about hardware caching, but you may also know about concepts like caching of web pages and things like that, and essentially it's the same principle. The idea is that we've got a piece of data that we're using, and we're going to keep that close somehow, and we're going to keep a small copy of it so that we can access it faster. In hardware caching, the basic principle is that we will have a big amount of slow memory, and this we usually just call the RAM or main memory. Then we will have a smaller amount of faster memory, and what we do is when we are using a particular chunk of the main memory, that will get copied into our cache, and then the CPU can work on the cache, which is faster to access while ever it's in that piece of memory. And then when it needs some other memory in RAM, it will simply copy the cache back and then get a new copy of a different location, for example. Now, what I've got here on the left is a particular example of a slightly more complicated cache that is nonetheless fairly common in CPU architectures. The idea here is that we have a main memory module, which will be a slower DRAM. Then we have 3 levels of cache. A level 3 cache, which is the largest cache. And then we actually have a cache of the cache called the L2 cache, which is again faster, smaller, and closer to the CPU. And in this case, we've actually got 2 versions of the highest level cache, the L1 cache. In this case, we've got a L1 cache for instructions and an L1 cache for data. So we can see that these principles of locality don't just apply to data that we're using, they also apply to instructions that we're using. And if we remember how the program counter works, where each time we increment the program counter when we're going through a naive step-by-step method through a set of instructions, we can see that we have high spatial locality in this case. So this video is just meant to give us a very brief overlook of some concepts related to memory that will be important for the rest of this course. So we discussed the fact that there are fundamental trade-offs between speed, size, and cost of memory. We also discussed that in many cases we have 2 forms of locality that we can exploit using a concept called caching in order to effectively increase the speed of memory that we have without sacrificing our ability to have larger memory, by having a big block of cheap, slow memory, cached into a smaller block of fast, more expensive memory that we have less of. So just to reiterate, locality was the idea that we can have some idea of data being close to the data that we've just used, being more likely to be used, either in terms of closeness in space or closeness in time, the idea that we may reuse the same data again. Caching was the idea of using smaller copies of a larger memory store so that we can use that in a faster memory store and gain a slightly better speed to size trade-off in our memory, but that we primarily get advantages from that when we have cases of locality.